last lecture about the main shaft of this helicopter. First, let's have a quick review about what we had last lecture. We said that we want to analyze this shaft of this RC helicopter. What we did at the beginning was we took off the shaft from the machine and we tried to simplify the shaft to this beam or to this shaft here. So we had one gear here at this one and another gear here which attached to the rotor at this point, and we have a couple of blades here at the other end of the shaft. And then we made an analogy between this question and one of the questions in Shigley's book, which is question number 23 in chapter 7. And we said that at point C and G we had bearings, so what can we do? We can put two reaction forces because of those bearings. And at point D there is a keyway and the gear is attached to the shaft at this point. And we have a couple of forces here that we found the resultant force and we put that one at this point. And also at point B here we have another keyway and the fan or the blade is attached to the beam or shaft at this point. So at the first step we found the reaction forces by writing Newton's law in y-axis and moment around one arbitrary point. Once we got the reaction forces, we used singularity function here and we wrote the equation for the moment for the shaft, and then we plotted the moment diagram of this shaft. And as you see here, from point A to point C there is no moment. From point C where the bearing is to point D where the external load is, we have a linear behavior for the moment, and then again from the load point to the other bearing we have another linear behavior, so and the rest is zero again. So our graph consists of three different parts: the zero parts for the first and last part, and one part with positive slope and one part with negative slope. And also we had a constant torque acting on the shaft from first bearing to the from the first keyway to the second keyway, from point B to point D. Okay, in this lecture we're going to continue our example by finding a factor of safety for potentially critical points of the beam. Okay, so that was the RC helicopter, and that was the analogy that we made for this question. And we said that we have one force here, one external force here where the gear is, and we have two reaction forces at the bearing, one here and one here. And in previous lecture we found the amount for these reaction forces. Okay, before I want to continue, I'm gonna review a couple of comments from Shigley's book. In 10th edition of Shigley's book, in page 361, it says that for a rotating shaft with constant bending and torsion, the bending stress is completely reversed and torsion is steady. Equations 7.7 through 7.14 can be simplified by setting mm and Ta equal to 0, which simply drops out some of the terms. What it means that, for example, if we have a general fluctuation like this means that we are having a fluctuation with an offset of, let's say, sigma m, and the amplitude is sigma a. Okay, and here I'm gonna I draw stress versus time. Okay, for this case, if sigma m is 0, that means there is no offset, and this is the case that we called completely reversed scenario. Okay, so when sigma m is 0, that it means that we are oscillating around time axis, and we go from completely tension to completely compression, and by definition this is called completely reversed scenario. Sometimes sigma a is 0. When sigma a is 0, it means there is no amplitude for this fluctuation, so our fluctuation actually it's a line. In another word, we have steady load, so in that case our loading is static. We don't have dynamic loading. Okay, now I want to change this stress to, for example, to torsion. If I have a torsion like this, I can say this is my mid-range torsion and this is the amplitude of the fluctuation. If the amount of torsion is constant, it means we have static torsion. So if torsion is constant, that means, for example, this is our torsion. This is t time. This means that TA is 0. We are here. And if I draw, for example, bending moment time, and if I see this behavior which is completely reversed, that means m mid-range moment is 0. This is what these lines wants to say. It wants to say that this one is 0 and TA is 0. Okay, there is one more thing that I want to mention here, and that is if I have this shaft with these supports like this and this loading F, this force makes some bending in this shaft, and we have two reaction forces here at these points. Okay, if this shaft is not rotating, so if the situation is non-rotational situation, in this case that's static loading, and we use our knowledge from static, from solids, and we analyze this question based on what we've learned in those courses. But if this shaft is rotating, so in rotational situation, what happens is here is at each point we face a completely reversed scenario. For example, at this point we are at maximum tension, but when it's rotating it will start to decrease to 0 and then go to maximum compression, and in another point we have maximum tension. So at each point we go from maximum tension to maximum compression. So at each point we see this behavior. we see a fluctuation around t-axis. So mid-range moment is 0, and when mid-range moment is 0, it means that we have a completely reverse scenario. Okay, so I'm gonna read this line again. For rotating shaft with constant bending, we are here, and torsion, I just want to focus at the first part. When we have constant bending, this bending is completely reversed, and when we have constant torsion, we are here, it means that torsion is steady, so TA is equal 0, and because of this one, mm is equal 0, so mm and TA are both 0 in this case. Okay. It is always necessary to consider the possibility of static failure in the first load cycle, and we can find that possibility based on this equation. What it tries to say is, we said that, and a couple of lectures ago, we said that if we start loading from 0, if that's my FT diagram, in a static type of loading, we can increase load up to a point that failure happens, and this will be our strength of that material. Okay, but we said that we can start increasing the load, and before that point start decreasing the load, and again increasing and decreasing, and after a couple of fluctuations we see that the failure happens. So if I compare this amount, I'll see that this is less than my initial force that I needed. So the required force here in the second scenario is less than the first one. It means that I could go to the failure with having less force acting on the material, and this is because I had a cyclic load on the material. In this line, it wants to say that we always need to check the first load cycle to make sure that our first load, which is this one, it doesn't pass the static failure. So we have to be lower than the static failure. If we have a behavior like that, that means we never go to the dynamic region, or we're gonna have a static failure. Okay, so figure 7.9, that's another important figure in this chapter, and it shows the different techniques to reduce stress concentration at a shoulder supporting a bearing with a sharp radius. In the first one, you see that the first method is called large radius undercut into the shoulder. So if we have sharp radius here, for example, we're going to have a large radius undercut here, so stress flow will go like this. So we're going to reduce stress concentration using this method. Another method is if we make a relief groove just before the bearing here, for example, before the shoulder, and it's called large radius relief groove into the back of the shoulder, like here. And a third method is when we have a large radius relief groove at this point, just before the shoulder. So these three methods can be used when you want to reduce the stress concentration at the shoulder. Okay. Now we can come back to our example. From last lecture, we found that, for example, if that's my point A, critical point A, point B, point C, point D, point E here, point F, point G, point H. From last lecture, we found an equations for moment, and for the first region that was 0, then it follows a line up to point D, then from point D and G is another line with negative slope, and from G to H is like a constant 0. And for torsion, we have a steady torsion from point B to point D. This is what we found in the previous lecture. And I can show you the numerical value for each point. The maximum point for the moment is 1459, and the unit here is pound inch for moment, and for torsion is the same as pound inch. So the maximum for moment is 1459 pounds inch, and the maximum or the only value for torsion that we have is 2532 pounds inch. Okay, and we have the amount of we have the amount of moment for point E and point F, which are 1115 and 845 respectively. Now we want to talk about the potential critical points. Okay, the first point that could be a critical point for us is point B, which we have a keyway at this point. Okay, if I look at these two graphs, I see that at point B there is no moment, and this moment is this moment causes a dynamic, let's say dynamic failure, and this one causes like static failure. Okay. So at point B, because there is no dynamic loading and there is just some static type of load, we assume or we expect that we're gonna have some static criteria involved when we want to analyze this point. Okay. I'm gonna start analyzing this point. The first things that at this point is important for me is the amount of shear stress. Shear stress, and we said that when we are talking about the stresses in this chapter, we mean the maximum stress. Shear stress is T times rho over second polar inertia. And because we are talking about the maximum shear stress happens when this fraction is maximum, and this fraction is maximum when this rho is maximum, and rho is maximum, this is rho. Distance from the center. Rho is maximum when is equals to r, which is the radius. So T was 25, 32. Radius, diameter was 1, so radius is 1 over 2. And J is P 1 to the power of 4 divided by 32. So after some simplification, we're gonna find 12.9 kpsi, and that's a maximum shear stress at this point. As we said here, because we just have some static loading, so we just need to check this question based on static points of view. So we're gonna use maximum shear stress theory from chapter 5 or chapter 4 of Shigley's book, and based on that theory, Ny will be Sy over 2 divided by shear stress maximum stress, and that was maximum shear stress. So Sy for this material is 57 divided by 2. This is 12.9, and the answer will be 2.21. There are a couple of things here that we need to focus about them. One of them is Sy that we used must have the same unit as our maximum shear stress. Otherwise, we had to put some conversion factor here. In this case, Sy is 57 kpsi, and SUT is 68 kpsi. We found these two information from internet or from some book, from some I'd say, for example, table 820 of Shigley, or you can find them online. This is a material property. Okay. So for the first scenario, for the first point, we used a static scenario and we found the n based on that. So n was 2.21. Okay. We're gonna go to the second point, point D, our second keyway. This point is also a critical point for us because at this point the moment is maximum and we have torsion. So this point sounds very critical to us. Again, if I come back to Shigley's book, there's a comment again, and it says that a keyway will produce a stress concentration near a critical point where the load transmitting component is located. The stress concentration in an end milled key, that's a important information for us here. The stress concentration in an end milled key seat is a function of the ratio of the radius r at the bottom of the groove and the shaft diameter d. So that is a function of r and d. For earlier stages of the design process, it is possible to estimate the stress concentration for keyways regardless of actual shaft dimensions by assuming a typical ratio of r over d is equals to 2%. This gives KT, theoretical stress concentration, 2.14 for bending, and KTS, theoretical stress concentration for shear, 3 KTS equals to 3 for torsion, assuming the key is in place. Okay. So based on this assumption, R over D is 2% for a typical end milled kiwi cutter. Okay. So in this question, D is given to us, and that's 1.75 inches. So I can apply this, I can plug this D into this equation and I can find the radius. So the radius will be 2% of D, which will be 0.35 inches. Okay. And KT is 2.14 and KTS is 3. The amount of KT and KTS are from this table. This table gives us the stress concentration factors based on the situation that we are in. For example, in this question, we are in the third line, end mill key set. So that is the concentration or assumption that we used, this one, and we didn't have any axial load. If we had one, we couldn't use this table because we don't have any value for this one, but we can use KT and KTS based on this table 7.1. Okay, let me we got the amount of radius 0.35, 0.035. So we are almost here. This is, let me delete this one. This is notch radius, the x-axis. So if we are here, we can draw a straight line. And we said that SUT of this material was 68 kpsi. So this is 60, so 68 is it's maybe a line, a curvature like this. Okay, so we can find the intersection and we can draw a straight line and read this number, and that will be our notch sensitivity Q. So for example, in this case, Q will be almost 66%. And we have another table for notch sensitivity for shear case scenario. Again, we're gonna find this number and we're gonna find the value for QS based on the graph. Okay, QS, which will be 72%. Okay, so KF fatigue factor is 1 plus Q KT minus 1, which will be 1 plus 66, 2.14 minus 1, which will be 1.8. KFS for shear will be 1 plus QS. KTS minus 1 will be 1 plus 72, 3 minus 1, 2.4. And we read this number and this number from table. And these two from another table, table 7.1, and these are from the table in chapter 6 for notch sensitivity. Okay. Now, if we come back to chapter 6, here we face a dynamic load, so we need to analyze a dynamic question. So we need to find endurance strength, and we said that in order to find endurance strength, first we need to find SUT, then we need to find SE prime, then we need to find SE. So SUT in this question is 68 kpsi, and we found that one from internet. Because that is less than the limitation that we had for SE. SE prime will be half of this one, 68 divided by 2, which will be 34. And SE will be marine factors Ka, Kb, Kc, Kd, Ke, Kf. This is lowercase k. This is uppercase k. So they are different. Se prime. So in this question, this is 0. This is 0. This is 0. This is 0 because it doesn't say anything about the reliability, it doesn't say anything about temperature, doesn't say anything about the other factors that could change the relationship between Se and Se prime. And all we have here is Ka and Kb, surface factor and size factor. For Ka, this is a property, this is related to the material. So this is the material property. And this is A SUT to the power of B, and A and B can be found from a table. So for this material, this is 2.7, SUT was 68, here to the power of B, B is minus, the exponent is minus 0.265, so the answer will be 883. And Kb is dependent on the type of loading. If it's axial, that's 1. If it's not axial, we need to find an equivalent diameter. In this case, because we have bending and the shaft is rotating, so DE, equivalent diameter, is equals D. And then we need to go to the table for DE, and we can find Kb from that table. It is D over 0.3 to the power of minus 0.107. So we can find the numerical value for Ka and Kb, and then we can put those numbers here, and we know Se prime, which is 34 kpsi. So at the end of the day, we can, from this one, we can find ingress and strength, which will be, in this case, 24.9 kpsi. Okay. Once we get ingress strength, we need to pick the criteria that we're going to use. For example, here I'm going to use Gerber criteria. In this criteria, as you see, if you want to find n, you need to use this equation. In this equation, n is a function of ingress strength and diameter. The amount of B and A can be found from these two equations. So, for example, in this case, if I want to find A and B, I said that mm equals 0 and TA is equal to 0. This is what I said at the beginning of the lecture. So this term is 0 because mm is 0, and TA, this term is 0. So the first one will be simplified to 2kf ma, and second one will be square root of 3 kfs tm, and I just need to substitute the amount of kf and ma here. So A will be 2 times 1.8 1459. So this is the number of MA, the amplitude of the amplitude of this fluctuation. So the answer will be 5.2.5 kilopound inch, and B will be square root of 3, 2.4, 2532, and the final answer will be 10.53 kilopound inch. And this number is the amount of, which is Tm, is the amount of steady torque on the material. So once I get these two numbers, I can substitute those numbers here, and I know about the ultimate strength, and I know about the diameter in this question, so I can find N from this equation. So after some simplification, N will be 3.59. In some other questions, we didn't use this line here, okay. In some other questions, you may be asked to design a shaft. And when we are talking about designing, one of the important things for us is to report or suggest some dimensions for the shaft or for the material that we're going to design. So if you want to design a shaft, with this equation, you can find, where did it go? With this equation, you can suggest some D. So that's used for designing when D diameter is unknown. Here we knew about the D, we wanted to find N, so we didn't use the second line. And we have closed form equations for N and D for each criteria that we're going to use. There is an alternative way to find safety factor when diameter is known to us, and that is when we find sigma A prime and sigma M prime based on these closed form equation. And once we get them, we can come back to chapter 6 and use these equations based on whatever we found here and find a safety factor. For example, here I used Gerber. So I could, instead of using those equations, I could find sigma A prime based on this equation. So what I needed to do, I needed to substitute diameter, MA, TA, we said that that's 0. So this one was 0. So I needed to find this one, and I needed to find sigma M prime. So we said that MM here, this is 0. So we just have this term. So we're going to find two numbers, whatever it is. For example, if let's say this is 10, this is 20. Then I go here and I substitute sigma A prime and sigma M prime, and I'm going to find N based on this equation. These primes here, it shows that we have a combination of loading on the specimen. So if I just have one type of loading, for example, if I just have axial, or if I just have moment, for this case I'm going to find sigma A and sigma M. For this case I'm going to find sigma A and sigma M. But when I have two or more than two type of loading at the same time, in this case I'm gonna find something like sigma a, which I call sigma a prime, and something like sigma m, which I call sigma m prime, like that. And once I get them, I can just do whatever I did in chapter 6. I can plot sigma a prime based on sigma m prime. I can use these equations, they are all valid. So in order to find safety factor, you can, when the geometry is known, you have two methods. One of them is find sigma a prime and sigma m prime and use the equation from chapter 6, or you can use the equation, the closed form equation from chapter 7, and just put the value inside your closed form equation and find the safety factor. It's up to you. Okay, another critical point that we're going to talk about is point E. Okay, we assume that the appendix 15, figure A15 14 that you can see here, this one, is applicable since the 2-inch diameter to the right of the groove is relatively narrow and will likely not allow the stress flow to fully develop here, because this is the 2-inch diameter. So what we can do here, we can say R over D, radius is 1, radius of the fillet, and this is 155, so this will be 0.65, and D over D will be, okay, where did it go? Okay, D over D will be 175 over 155, and that will be 1.13. So knowing these two values, we can come to this table. R over D is 0.65. So for example, we are something here, and D over D is 113. So if this is 10, so the line is somewhere like that between these two lines, and we need to draw a straight line and find the intersect and read the number here. So for example, if this is 2, in this case I'm saying that my KT is 2.1. Okay. And I can go to the tape to the figure 620, the Q notch sensitivity graph, and I can find Q based on that one, the same thing that we did for point D. So Q in this case will be 76%. Then I can find KF based on Q and this KT, which will be 1 plus Q KT minus 1. So in this case, this KF, the numerical value for that one will be 1.8. Okay, so Ka is the same because that's a material property. So that is what we found in the first step, 839. Kb in this case will be the diameter, which is 1.55 divided by 3, and this is 0.107. So Kb will be I think my computer is tired. Okay, Kb will be 0.839, and then we can find Se by multiplying Ka, Kb, Se prime. The other factors are 0, so Se in this case will be 25.2. Okay, and once we get that one, again we can use the same equation that we used for in the previous step, and we can find A, we can find B. So in this case mm is 0. We're at point E, mm is 0, okay, and TA is 0. This is what we discussed about in the previous step, but at this point, as you see, we don't have any torque, any torsion at all. So Tm is also 0. So there are so many zeros in the equation, and this gives us, if I showed you, like here, if where were I? Okay, if mm is 0, we don't have this term. If tm is 0, we don't have this term. So b will be 0, and a will be just 2 times kfma. So what I can do, I can easily find I can easily find let me just write the final value for a and b. That's kilopound inch, and I just said b is 0. So with these two values and using that equation, we can find n, which is 447. Okay, and as I said, mm is 0, t is 0, so TA is 0 and TM is 0, because at point E, after a point F, at point E, I don't have any torque. Okay. The other critical point, shoulder at point F, just after this 2-inch diameter in the graph here. So at this point, R over D is 0, 1, 25. I just recalled something that just wanted to double check that you know that when we are at point E, this is the amount of moment. This is MA that we have to use in A equations. So when, for example, when I wanted to find A at this point, I said A is equals to KF MA, and that was 2 times 1.8 times 11, 15. And the answer was whatever I wrote that for you. Okay, that was obvious because we were at point E, so we had to use the the corresponding moment value for the for the moment at that point. Okay, for point F, R over D is 0.125 over 140, so that will be 0.089, and D over D will be 2 over 1.40, so that will be 1.43. So if I come to this graph, because you see I have a bigger diameter like this one, this is 2 inches. In my case, this is 2, this is 2 as you see here, and then I have fillet here. So I'm gonna analyze this part. So I'm gonna use this graph here. Okay, so from this one I can read KT. R over D is 1.25, so I am somewhere 1.125. I am somewhere here, for example. Oh, where did it go? I am here. D over D is 1.43, so if it is 1.5, I am almost this one. So if I go up, I can find this intersect, and then I can come here. So I have to be a little further, so it's almost 1.7. Okay. We are not very picky when you want to read these tables, so just read the value that looks fine to your eyes. And I'm gonna go to the Q table, and I'm gonna read the Q with the same method like that. And again, like once I get these two values, I can find KF based on this KT and this Q, which in this case will be 1.5. And I'm gonna find SE by multiplying KA, KB, SE prime. We said that the other marrying factors here are 1. SE prime in our case was 32. KA was the same thing that we found in the first step because it's a material property, so it doesn't change in every step, so that's Ka. But Kb is depend on the load and depends on the diameter, so it's different for each part. So in this part, Kb is 1.4 divided by 30%, and the exponent is 1.107. So in each step, the denominator, which is the diameter, is different because at each step we are analyzing different parts. So we're going to find different KB. Ka is the same. Se prime is 34, so we're going to find Se at the end of the day, which is 25.5 kpsi. So my SE was found 25.5 kpsi, and in this case, okay, and in this case, when we're at point F, there is no torque, so T is 0, so there is no amplitude and no average mid-range torque, and mm is 0 because we said that if that's m, that's t. We are facing completely reverse scenario, so we are fluctuating around x-axis, so mm is 0, and ma is this value 845. So with this information, we can find a, which is 2 times capital Kf ma, just for this case when this simplification is done in the formula. It will be simplified to this equation, and I can say this is 2 times 1.5 times 845, so the final answer will be 2.535 kip inches, and b will be 0 because t is 0 and mm is 0. And we're going to use the same equation, and we're going to find safety factor, and this time that will be 542. Okay, so we analyzed all the critical points for this problem, and for each point we found one safety factor. In the next lecture, we're going to continue this example by finding the deflection at each point, and then we can check if the deflections are acceptable or not. If you have any questions, or if you think that you may need the notes, feel free to send an email to engineeringfun2016@gmail.com. And thank you for your patience. See you next lecture.